Hi, welcome to our talk. My name is Desmond, Liu Zhenyuan. I'm a research intern at the Institute of Science and Technology, Austria. Today I'm going to be presenting our work on worst-case rigidity analysis and optimization for assemblies with mechanical joints. This work is done in collaboration with Jingyu, Xu Wing from the Chinese University of Hong Kong, and Peng from Singapore University of Technology and Design, and Zhang⁴ from Hasso Plattner Institute, and Bernd, who is my current supervisor from Institute of Science and Technology, Austria. So let's begin with a little bit of introduction of what's going to be at the center of our stage today. That is the assembly structure. So in real life, people are making use of assembly to build all different kinds of amazing things, like mechanical objects, for example, this car engine, or deployable structures like deployable cables or foldable chair, and toys like this Lego Technic airplane. However, when it goes to deployment, there is a very important concern we need to address. That is the structural rigidity of the assembly structure, because that's a very important factor of how durable the structure is in real life. Let's imagine we are trying to design this kind of assembly structure and we want to deploy it in some children's playground in a park. And as the designer, I think it's very important to ask these two questions: how rigid the assembly structure is, and if there's a way to make it more structurally rigid. I think this is very important because as the designer, probably we don't want our structure to be too easy to deform or easy to fall apart or break, especially when we have a lot of kids to play around it and do crazy things to it. So it would definitely be nice if we can design really rigid assembly structure. However, designing rigid assembly structure are kind of a hard job, and one of the most important reasons for that is because of those mechanical joints in the assembly structure. So mechanical joints, they not only just connect different parts together, but at the same time they will also allow different kind of rotational degrees of freedom and translational degrees of freedom. Let's check out a few examples in 2D and 3D of mechanical joints. So like in 2D we have hinge, prismatic joint, and sliding joints. And each one of them has different kind of rotational degrees of freedom and translational degrees of freedom. And in 3D, it's gonna be even more complicated because in 3D, we can have up to 3 rotational degrees of freedom and 3 translational degrees of freedom. So there are all different kinds of mechanical joints, and it's not a trivial task to come up with a systematic way to model all different kinds of mechanical joints at the same time. However, different kinds of mechanical joints are not the end of the story. If we really want to model joints in real life, we have to consider another very important phenomenon. Let's check out this example. So now we have 2 Lego Technic parts putting side by side, and we're gonna connect them using 2 Lego Technic pins. So if we just use our common sense to reason about it, probably we'll say, okay, so this very simple assembly is rigid because we have 2 pins and they're gonna cancel out all the rotational degrees of freedom and translational degrees of freedom between these 2 parts. But let's check out how this will work in real life. So as you can see, we're trying to apply some force on the 2 ends of this very simple assembly structure. And you can see the structure deform quite a bit, especially around the joint. This is because of a very notorious effect called joint jitters. So this can come in for many reasons. Maybe the joint itself is not very rigid, and there might be some fabrication error. But if we really want to design assembly structure of more than, say, 100 joints in real life, it's definitely very important to take this into account if we really want to design assembly structure of great structural rigidity. And if there's a way to model all the different kind of things using some existing work, so let's quickly check out some existing technique to address structural rigidity. And the first thing we might try is to use Tensegrity Model. And this is a very classical model. And in this kind of model, the parts are either modeled as incompressible bars or inextensible cables. However, this might not be totally sufficient for our use case because they only support position constraints, and it's kind of hard to support all different kinds of mechanical joints we mentioned on the previous slides. And another approach we might want to try is to use finite element method. So the way we're gonna use this is to prescribe some loads, and finite element method is gonna compute the stress distribution over the whole objects. However, prescribed load cannot be so straightforward in some use case. For example, like this assembly structure in the park, and there might be different kind of way to apply the loads to it, and it's kind of hard to argue which one might be the best one to give to the algorithm as the input. So it would definitely be kind of nice to have this kind of algorithm that take only the assembly itself as the input without the prescribed load, and it can model the parts as elastic body and model mechanical joints of different kinds, and answer these two questions: how rigid the assembly structure is, and if there's a way to make it more structurally rigid. And this will correspond to three technical contributions in our work. The first one is our modeling of mechanical joints. We can support mechanical joints of arbitrary combinations of rotational degrees of freedom and translational degrees of freedom, and also the joint jitter effect. And the second contribution is our worst case rigidity measure without prescribed load, and this will help us to answer how rigid the assembly structure is. And on top of number 1 and 2, we can come up with some optimization method to reinforce the assembly structure to make it more structurally rigid. So let's dive into our method. In this section, I'm gonna briefly talk about how we model the parts and mechanical joints in the assembly structure, and how we formulate the worst case rigidity as a minimization problem and solve it using eigenvalue analysis. So the first thing I'm gonna talk about is the worst case rigidity, which is also the central concept in our algorithm. And let's begin with a little bit of preparation. We will first model the parts as elastic bodies using finite element method. And we're gonna model each part as the stiffness matrix so we can incorporate the material property we want. And then we can define our elastic energy as a quadratic function of the nodal displacement. And here we're gonna denote the nodal displacement as delta x and the stiffness matrix as k. And then on top of that, we can further define our worst case rigidity. The idea is to find the direction of displacement that causes the smallest amount of elastic energy. So in other words, we want to find the direction in which we can deform the structure in the most energy efficient way. So we want to minimize this elastic energy over all possible direction of displacement. And following that idea, we can formulate the problem into this kind of minimization problem. However, up to this point, we still have a very important piece missing, which is the join constraint. Because we're dealing with assembly structure instead of a single monolithic object, it's very important to figure out how shall we model the joints. So just to remind you, in this work, we aim to tackle different kind of mechanical joints, and they will allow different kind of relative motion between two parts. However, our insight of modeling them is like, rather than think of how the joints allow specific relative motion, we will think of how the joints eliminate specific relative motions. Let's take a look at this hinge joint, for example. So rather than think of how the hinge allow the relative rotation with respect to the rotational axis, we'll think of how the hinge eliminate the relative translation between these two parts and the two other relative rotation between these two parts. And now I'm gonna briefly talk about how we implement this idea. For more details, please check out our paper. So the first thing I'm gonna do is we're gonna sample some nodes from each part connected by the joint. Because we're in 2D, it's sufficient we just sample 2 nodes from each part. And then we're gonna reason about all the relative motion that is allowed by the joint of these 4 nodes. That will include the rigid motion, the allowed relative motion, and the individual part deformation. And after we find out all the motion that is allowed by the joint, we can take the null space or the complementary space of all the allowed motion, and that will give us the motions that is not allowed by the joint. And those are the motion we want to eliminate from the solution space of our minimization problem. If we do this for each joint in our assembly structure and aggregate them together, we will get a join constraint of the form A delta x equal to 0. This is kind of like a hard constraint. By doing this, we didn't really take into account of this join jitter effect. Because by doing this kind of hard constraint, we actually assume the joint itself is perfect. All the motion that is not allowed by the joint shall be perfectly eliminated from the solution space. However, in reality, because of the existence of the joint jitter, that is in general not true. For example, this hinge joint is supposed to cancel out all the relative translation, but because of the joint jitter, we can still see a little bit of joint jitter happening on the joint. So to tackle this kind of problem, we're gonna convert the linear constraint, this card constraint, into this kind of energy penalty term. The way we're gonna do this is we're gonna square the linear constraint. And in between, we can add in controllable weights to control how soft or how hard each degrees of freedom of each joint is. So if we have a very large weighting term for corresponding degrees of freedom on a joint, basically that will mean we're trying to model that joint as a hard constraint if we set a value to be really large, say approaching infinity. On the other hand, if we set a weight to be kind of close to 0, and that will mean that corresponding degrees of freedom of the joint is kind of soft. It's easy to deform. So in our paper, we come up with a data-driven approach to select the weight based on the simulation and the physical experiment. For more details, please check out our paper. And by doing this, we can call the matrix A transpose as A as J, and then we can add an energy penalty term into our objective function. And that will convert the problem into this form. So actually we know we can use eigenvalue analysis to solve minimization problem of this form. In our case, the smallest eigenvalue will be the global minimum of our optimization problem, and the associated eigenvector is gonna be the minimizer. So according to our eigenvalue analysis, the smallest eigenvalue is gonna be the worst case rigidity, and the corresponding eigenvector is gonna be the worst case deformation. And on the computational side of view, there are two things I think that's worth mentioning. The first thing is we're dealing with a sparse system. Both the matrix K and J are sparse matrices, and their summation is also sparse matrix. And another good thing about this is the eigenvalue decomposition is differentiable, and we're gonna make use of this to do continuous optimization, and we're gonna talk about it a bit more later. And here's a little bit of visualization to help you understand what's going on in our worst case rigidity analysis. So let's consider this very simple 2 bars assembly structure with the top node connected via a hinge joint. The other 2 ends are fixed to the ground. So we are trying to study how the elastic energy change with the displacement of the top node. And by using our eigenvalue analysis, we will find out that the smallest eigenvector actually corresponding to the direction in which we will get the smallest curvature at the origin. And the smallest eigenvalue itself will be the smallest curvature at the origin. And with all the worst case analysis set up, we can try to do some optimization on top of it. The first thing we might try is to use gradient descent to optimize the geometry of the assembly structure to make it more structurally rigid. And in this boomerang example, we're gonna parameterize the boomerang by the endpoint of the inner supporting bars. And then running gradient descent, we can get the boomerang converged to a more structurally rigid configuration. So basically it will move the endpoint of the supporting bars from the end of the boomerang towards the center. And later I'm gonna show a physical validation of this example so we know it's actually working. And another example I'm gonna show is the topology heuristic. So we're gonna use this heuristic to suggest new parts for the user to add. And the way we're gonna do it is we're gonna compute the difference of displacement per node pair. And then we're gonna compute the projection on the parts we're trying to add and sort all the candidates by the length of the projection in descending order and report the top K candidates to the user for them to choose which one to add to the assembly structure. And in this case, the long K projection will be this, and that might be the one the user want to add to the assembly structure. Okay, so with all the worst case rigidity analysis and optimization methods set up, we finally get to the results section. So we prepare a bunch of examples, and their initial configuration is not very rigid. And after we use our optimization methods to reinforce it, they become much more rigid. And let's check them out. So the first thing I'm gonna show is this Bernd model. And in this Bernd model, we have more than 80 parts and 100 joints, and we use Lego technique assembly to build it. And after we run the worst case rigidity analysis, our algorithm reported that the vulnerability will happen on the wings of the bird. So that would be the worst case load shown in the yellow arrow. And so correspondingly, we'll use a horizontal beam to reinforce the wings of the bird. And let's see some video footages for comparison. And you can see under the same weight, the reinforced model undergo much less deformation than the initial configuration. And we have an even more complicated example using Lego technique, which is this car chassis. It has more than 150 parts in the initial configuration. And our method still computes the worst case loads and suggests new parts for us to add. And we use some new parts to reinforce the car chassis to make it more structurally rigid. And let's check out the photos for comparison. On the left, it's the initial configuration. And we can see like the parts pointed by the red arrow is severely tilted after we're applying the weights. However, after we reinforce it using the new parts, we can see the horizontal beam basically just stay horizontal under the same loads. So the whole car chassis is much more stable or much more structurally rigid than it was before. And we also tried some continuous optimization. So here's the boomerang example again. We have this boomerang example, and we want to use the gradient-based method to change the initial supporting part. So basically, we just run the gradient descent, and the inner supporting bars converge to a better position where we have a better structural rigidity. And here is the photos for comparison, and we're still trying to apply the same loads to both assemblies. And we can see like the reinforced assemblies undergo much less deformation than the initial configuration. And here's an even more complicated example using 3D printed parts and Lego technique pins. So the bunny example is even more complicated than before, than the boomerang example, because the silhouette of the bunny itself is not rigid. So we have to add this inner supporting structure to cancel out all the free motion happening on the silhouette of the bunny. However, if we just arbitrarily add this kind of supporting structure, the whole silhouette might not be at the most rigid configuration. So we run the gradient descent algorithm to make the structure more structurally rigid than it was before. And here is some footages for comparison. And you can see we're trying to apply the same weight, which is a bottle of water, to the silhouette of the bunny. And the initial configuration, you can see the deformation compared to the optimized one is much more perceivable. So our gradient-based method works pretty well in terms of reinforce the silhouette of the bunny. And then we have some 3D printed example. And in this rack example, we use 3D printing to print out the parts as well as the joints. And our worst case rigidity analysis told us, okay, so the worst case loads will happen on the side of the rack. So we correspondingly add some horizontal beams to support the side of the racks. And we can see in the video footages under the same motion, the rack getting much more rigid than it was before in the initial configuration. And the final result I'm going to show is this boat model. So we're using magnetic sphere and some metal rod to build this boat model. And the initial configuration is not rigid at all. So it has this free motion. The two ends of the boat can just go up without costing much energy. So after we run our worst case rigidity analysis, we detect this free motion, and we try to add two new beams to the boat model, and we make it much more structurally rigid. And here's the videos for comparison. I guess if you go on the right, you will prefer to choose the boat on the right instead of the one on the left, because it looks much more safer. So that's the last example I'm gonna show. And before I close, and here are some concluding remarks. So just to wrap it up, the whole thing a little bit. So we propose worst case rigidity for assembly structure with mechanical joints of arbitrary combinations of rotational degrees of freedom and translational degrees of freedom, and with joint jitters into account. And on top of that, we also built 2 optimization methods to strengthen the assembly structure for better structural rigidity. However, there's also a couple of limitations, and it would be cool to see them getting resolved in future work. The first thing we didn't take into account is the functionality of the assembly structure, because some assembly structure, they have this kind of intentional degrees of freedom or intentional free motion because they need to accomplish certain tasks. And we didn't take into account this kind of functionality constraint while we optimizing for better structural rigidity. And another direction to go is trying to support more types of joint, especially those types of joint depending on the contact and the friction. For example, this kind of woodwork joint. It would definitely be cool to see more joint getting supported in our framework. And another direction is just trying to support friction, which in our work we didn't consider. So if we can manage to finish these 3 tasks, I believe it's going to be a huge step forward towards designing rigid assembly structure that's suitable to deploy in real world. So with that, I will close, and thank you very much for your attention.